welcome back. Let's talk about some of the background of this whole cell matrix project. This was started in 1986, late spring, by Jimmy Hargrove, Larry Henry, Morley Raju, and myself. A number of conversations we were having about a variety of different things. Now, this was the 80s. Artificial intelligence was back in vogue. So we were all talking about self-consciousness, self-awareness, the idea of machine learning and things like that. We were also talking about the idea of where the line between hardware and software comes. So particularly Jimmy and myself and Larry, we were working on a machine called the VAX 11780. And the VAX 780 was a microcodable machine, meaning that the hardware level itself, where you interpret, where you execute assembly language instructions, that was actually interpreted by a smaller machine sitting inside the CPU called a micro machine. And so what you thought was actually hardware that was executing machine code was actually still just software. It was a program running, executing your actual machine language opcodes. So we were having discussions about where is the line between hardware and software, and what's the softest machine you could make. You can make a machine where the actual machine language is not being processed at the hardware level, but at a software level. So how far could we push that software level down? How small could we squeeze the hardware in? There were a number of other things going into this mix, but a lot of philosophical discussions, a lot of questions about limits of computation, Turing computability, halting problems, and things like that. And one day, I believe it was around March 1986, Morley Raju came to me before a class. I was taking a course with Larry Henry in VLSI Design for Testability. And Morley came to me right before a class, and he asked me the following question. He said, have you ever written a program that can print out a copy of its own source code? And he'd been trying to do this for a little while, and he was kind of stuck. So he asked me this question, and I went into class, and I sat there during this lecture on design for testability, and I pondered this question, and I started scratching out some code. Now, to do this challenge correctly, you need to have a self-contained program. You're not allowed to read your program in from a disk file, for example. That's cheating. So the idea was, could you write a program that would just self-contained, in a self-contained way, be able to output its source? So the first thing you try is something like, this is a basic version, 10 print, and you put double quotes because you're going to print out a string, and you just start printing the source code. So what I want to print out is the character 10, a space, and then print. And then a double quote, which inside quotes I have to use 2 double quotes. And then I need the rest of the string, 10 print. And then I need to do 2 double quotes, which I need to double, so I have 4 quotes, and so on. And as you start trying to do this, you sort of get into this infinite descent where you find that you're making a longer and longer print statement, but you're not actually getting any closer to finishing this problem, to being able to actually print out your source code. So then you scratch that, and you try using a string. So, and again, this is old style basic programming. You might say A equals 10, print a string. And this might be statement 5, and statement 10 might be print a string. So when I get to statement 10, I'm going to successfully print out this part of my program. But I haven't printed out this part of my program, so maybe you want another variable up here, and maybe you want to say something like a string equals 5, a string equals quote, and then you start getting into the same problem again, where you keep writing a longer and longer print statement, but it doesn't actually get you anywhere. So this is a good exercise to think about, and it's a pretty straightforward thing to do if you go off in the right direction to solve it. But it's a good thing to ponder, and it was really in pondering this that the architecture for the cell matrix came about. So you can stop the video and think about that for a while if you like, but I'm going to go on here. And I'm not going to show you the code that we used. You can download that from the course site. But the trick turned out to be to to create a big string variable that mostly contained your actual program, and then to print it out twice. To print it out once as a string variable and once as what would be the actual executable code, and to do some special handling when you got to things like double quotes, that you needed to have two of them inside a string, or since this was actually done in C, backslashes were special. If you wanted to print out a backslash, you needed to print out two backslashes. So you can download the working version of this and you can see how it actually worked. But anyway, the solution of this puzzle led to some more discussions, and it brought us to the idea of defining a basic hardware unit that could be used to make a general circuit by simply reconfiguring it. Alright, so that was sort of the background that went into this, and once we had a basic cell definition, Larry and I were already taking this VLSI course, and the course had money to actually fabricate chips. So we needed a project that was related to design for testability, but we really wanted to build a cell matrix, which was originally called the PIG. PIG standing for Processing Integrated Grid. So we wanted to build a hardware prototype of the PIG, and we came up with the idea that if you built this collection of cells, you could use cells from one region of the system to interrogate cells in another region. And so in some sense it was the ultimate in testability, because we could use a few cells on the edge of the collection to access cells that were not immediately available. So we could build scan paths to go in and interrogate internal cells and run tests on them and then report back to the outside world. So we got permission to fabricate this for our class, and we manufactured through Moses a number of prototypes. They were on about a 2 centimeter by 2 centimeter die, and we had a total of 12 cells on each chip. So it was a 3 by 4 matrix of cells. Each cell was about 2,500 transistors, so one of these chips had around 30,000 transistors. It was actually 30,001. We put in a few extra transistors just so we could say it had over 30,000 transistors. Alright, so that's the backstory. The next video I'm going to talk about how you actually, what the cell actually looks like, so that you can use it to build general purpose logic by programming it.